In order to approach cybersecurity for PLCs, modern PLCs, we really need to understand what's happening during PLC execution, what's happening in the programming stack, and what are the different components that work together towards implementing the control process. These slides provide, again, the stack. You have your hardware, you have your operating system, and what I discussed before, the PLC runtime that is responsible for executing the PLC code itself, like the PLC binary, that, as we saw before, using ladder logic or structured text, you compile it to a binary that can be again machine code or byte code to be executed by the runtime. At the same time, a modern PLC would have a few more services. It can support FTP access, SSH, web server, as we saw before in the case of the Wago PLC. So the runtime runs more than just the PLC binary code. It runs other services as well. As I color-coded proprietary and open source. So proprietary has this more yellow color, open source has a more green color, and Linux, for example, itself with the real-time paths, that's an open source. It's an open source software, so you can actually again inspect the code, find vulnerabilities, and there are patches that everybody applies. Well, you can apply when you have a security problem. The proprietary side happens within the vendor. For example, the PLC runtime is proprietary to the vendor. The way the PLC is executed, it's being loaded to the runtime and then executed at the OS level, at the hardware level, is proprietary. So the mix of the two is creating interesting security questions because this has a different way of how security is being addressed. Because it's open source, there are many eyes looking at it, you find vulnerabilities easily, but you also fix them much more easily and others are doing it for you. So the 0 days may appear more in the open source world, but they're also being passed and being fixed quickly by the developers of the libraries. On the proprietary side, because again, this proprietary, it may be harder to find vulnerabilities, but then once this is done, then it may take some time for the understanding on behalf by the vendor. At the time vendor realizes a vulnerability has been found, it's been exploited in the wild. So the proprietary side, again, pros and cons with open source, and there's a modern programming stack for the PLC would have components from both sides. So during your security, building your security architecture for ICS, you have to ensure that you understand both sides, what is proprietary, what is open source in the system. And there could be, as we saw in the first lecture, there could be way more open source components that we think in the system. So for example, you may have your runtime, and the runtime could have OpenSSL, that it is an open source library, and then it has Apache, it may have Python support, or other open source repositories that the vendor just brought into their own ecosystem and complemented with their own custom code for the runtime and their own custom compiler for the PLC code. How does the PLC code is converted to the binary? And it could be some things that are all some services that are also proprietary and more vendor generated. For example, Modbus communication, Modbus TCP, or other forms of industry-specific communication protocols could be implemented by the vendor themselves and not just port them from open source repositories. So here, compilers, the GCC, so whatever GCC brings into the table in terms both of problems, vulnerabilities, and for protection are applicable. And there's also the presence of a custom compiler on behalf of the vendor that takes PLC code and produces the PLC binaries. So security, again, in this context has to be understood at all levels, right? The proprietary and the open source, at the operating system level, at the software level. The PLC runtime is just a regular C++ process that has been compiled with a regular compiler. So any vulnerability applicable to regular software is applicable to the runtime. The buffer overflows, there could be heap spraying attacks, all the attacks you may have seen in application security, if you've taken the course, are applicable to the runtime. So the surface, the attack surface of the operating system and the runtime itself are familiar IT attack surfaces. And on top of that, you have a custom compiler, and this one has not been heavily vetted by the community, in contrast to GCC, for example, that if there's any vulnerability stemming from GCC, you can easily you can find it and then fix it and patch it in the next version of GCC. Here, if the compiler is producing something that can be exploited, it may take longer to be understood and be patched on the PLC side. So the custom compiler here, and then this code, again being proprietary, is also causing delays in security assessment and security fixing of any vulnerabilities. To expand more on the two components that are the most interesting here, the most interesting part is the PLC binary code and the PLC runtime, because this is regular operating system, this is again regular software, but what we want to emphasize more and understand a bit further, because this is an OT specific class, is the PLC runtime and the PLC binary side. So starting with the runtime, as I mentioned already, the runtime is just software. You write it in your regular languages, C++, and that means whatever GCC can do for you and can do against you is fair game. So if you can enable StackGuard through GCC, then you have some extra protection given to you by the compiler, or you have some kind of a component that checks all your memory accesses and tells you whether you may have some buffer overflow problems or not. That's also things you can use in your runtime. And again, the runtime can be exploited in a very similar way to all regular software and all regular vulnerabilities we have seen in the wild. But what's unique about the runtime is the fact that it typically runs with full privileges. Because the runtime is also direct, even though there's an operating system, the runtime has its own proprietary stack that has low-level connection to the hardware. It taps into the hardware and also to the network itself. So to be able to do all these things, it typically runs with full privileges as root or super user. And it makes sense to an extent because there's no multi-user environment, that you have your kernel and you have your users, that they should not be able to access the kernel libraries, and there's natural separations in memories, in processes. Here, the runtime is the only thing that runs in a way, and within the runtime we have the rest, and it has to run with full privileges as it accesses low-level hardware. At the same time, this is bad because if you manage to take over the runtime through some kind of vulnerability, then you take over the whole system. If you in regular IT, you manage to take over a user process, you can only affect only that user process, and it's very difficult to escape and do privilege escalation from there. But here, since this is root already, if you manage to take over through some vulnerability and you manage the remote code execution that leading to privilege escalation or leading to running custom code, that means you can fully take over the system. And since this is regular software, as we said, there have been vulnerabilities. I have an example here in Codesys, how many vulnerabilities have been reported for the runtime directly. So not for other parts of the framework, but of the environment, but for the runtime directly. So you can see from 2018, 2020, how many security updates have appeared for the Codesys environment. And let me make a note that this doesn't mean that Codesys is bad framework or bad software. It's good that the framework developer is publishing regularly advisories. That means, because no software is perfect. So if they had 0 updates, security updates, that would be more sketchy in a way. So the fact that they discover this and they fix them means that they're doing the right process. But it also shows that the runtime is sensitive, the runtime is software that can be exploited. So you have to think of also complementary methods towards protecting your OT environment. The negative side is running with full privileges. The positive side is that since the runtime is regular software, which was bad in the past, what's good about it, you can also find vulnerabilities with conventional methods. So you can apply, for example, fuzzing in order to find vulnerabilities in the runtime and fix them. And actually, that's some research we've done at NYU, that we took some of the runtime libraries on how it reads the K-bus, that's the interface to the input-output, sensors and actuators, or things like how are other threads being created and how you communicate with the PLC data. And we fuzzed the functions and we found crashes. So fuzzing very quickly it means fuzz testing, and you provide unexpected inputs to the function and see how it behaves. So, for example, I'm asking, what is your name? And you say, -1, right? -1 is an unexpected input for a name, and your program, because it doesn't expect that, it may crash. So this crash may be an indicator of vulnerability. It could be a way for the adversary to use the crash as an initial exploration to find some more advanced exploitation method that could lead to maybe system takeover, or even the crash by itself is a denial of service attack. So by fuzzing the functions, you can find vulnerabilities and you can fix them in the next version of your runtime. So that's the good side of the PLC runtime being regular software. You can use regular software methods to enhance its security. On the PLC binary side, remember we have the runtime, that's regular software, that executes the PLC binary, that is the specific control logic that we want to implement. And that's a custom binary. The PLC runtime is regular binary, the PLC binary is a custom binary. It's been compiled from PLC languages like ladder logic, structured text, and that binary may be special, but still maintains some properties of a binary. So it has assembly instructions, but it's not an ELF binary. It's not your standard library to be loaded by your standard loader. It could have assembly instructions, regular assembly instructions, or bytecode in case of Siemens. Siemens has a bytecode representation. The Codesys framework is producing directly assembly instructions, and also has low-level memory operations. So the PLC binary may be special, but some things can be ported. For example, buffer overflows, out-of-bound writes, integer overflow are still applicable to some extent, especially for structured text that looks like regular languages. It brings also vulnerabilities from regular languages. Memcopy, string copy, these functions have been notorious for causing problems, security problems. Maybe they don't have bounce check, that's why they may lead to a crash or not. And we did some initial exploration at NYU to understand how the PLC functions can be exploited or not to cause some crashes. So some actually are crashing, some are not. Bounce check, some are doing bounce check, some are not. So still this environment is being, it hasn't followed the security practices of the IT world, where you have the secure version of scanf or the secure version of how you get characters from the user. So the fact that these are could be vulnerable functions, and there's a potential of the attacker taking over the binary, leading to taking over the runtime, leading to taking over the system. So you can create a chain of events that allow you to attack the system. On the good side, again, for PLC binaries, these binaries are very difficult to exploit. And going back to the threat modeling, you may want to completely ignore that if you think that's too costly to be directly defending your PLC binaries. So these binaries have limited complexity. Typically, they're typically mathematical functions. There's an input, there's some kind of processing like absolute value or saturation, or PID as more advanced ones, and some output is produced. You rarely have array manipulation, string copies, mem copies. So most of the binaries we have seen have limited complexity, so they don't have those vulnerabilities we saw before. And actually, it's mostly structured text. That specific way of programming, not the visual one, but the programming one, the more looks like regular programming, that's the one that has the C-like vulnerable functions. The other languages don't have them, so you cannot use those avenues to exploit the PLC. As I said, not much memory array handling. And once you attack the binary, you may do something to an extent, but then there's a runtime that in a way acts as a sandbox. So if you are to attack the system through the binary, you have to escape the binary first and then escape the PLC runtime to go to the system level. So that's an extra hop the attacker has to go through to be able to have persistence, or an attack that maintains its presence even after a reboot or some kind of other mechanism. And last thing here is that PLC binary, the payload is difficult to deliver. When you have a buffer overflow, typically there's a parsing you have an input and you give a longer input that you should, and in that input you may hide your payload if you have no execute bit disabled. So in the case of the PLC, you don't get a direct input from a user. It's not like type your name or type your age or gender. You just have input coming from a sensor, and these are typically numeric values. So the payload, to be able to craft your assembly, your chain of assembly that leads to running execv, for example, system call for execv to get a terminal, a reverse shell, you need to send very carefully crafted code, and that may not be easy if you only have sensor input coming into your system to be able to manipulate the sensor to be producing an exact payload. Still, we need to understand if the PLC binary is protected. Even though it's difficult to exploit, there are things that could be done. For example, manual inspection of the binary, fuzzing the binary as well, and patching the runtime to make sure that any PLC binary exploitation cannot escape the binary, the runtime to actually take over the system.